Thank you very much for taking the time today to view our video. Before we begin, we'd like to take a moment to introduce ourselves. There are many aspects to 9.Connects, but it boils down to the fact that we're a PCB-centric organization. We believe and focus on the PCB due to the fact that it is truly the center point of all electronic design. That's where our expertise lies. We provide services not only in the PCB layout, but in design consulting as well. And during the technical portion of this webinar, you will see this expertise in motion. For more information on our services and past webinars, please contact us. Our information is listed in the description below. Thank you for giving us a moment of your time, and please enjoy the presentation.
We want to start a series on switching power converters. There's a whole bunch of misunderstanding about them. A lot of people just buy one and stick it in and it works fine, but it turns out there's a lot of places that they can fail, and there's a lot of people who are having difficulty knowing, well, how do I lay out a PC board? Or I can't find the one that does exactly what I want, so I have to actually make one. And sometimes the app notes just don't quite take it as far as it needs to go, and they want to be able to understand really what's going on inside and also know what the limitations are, like, well, how do you choose an inductor, and what's a good inductor and a bad inductor, and what are the issues with bypassing components, and how do you route the PCB, and what should you be thinking about? So this series is going to start with that and work on the various aspects of that. We're going to again try to make it more intuitive and stay away from real heavy design theory, but try to make it to where it's understandable so that people can understand what's going on in both the signal integrity and the layout portions of it. Okay. Again, we want to understand how switching power converters work. We want to be able to provide a consciousness and thinking about electromagnetics and signal integrity as people embed these and also practice working on them and designing their own. And in order to do that, we need to have a framework upon which you can build. You need to be able to think about things in a way that makes sense. We're also trying to open a box of possibly new vantage points on how to look at things that will really help you to be able to become more effective on that. And in order to make this area feel more intuitive and hence welcome, we're going to try to speak to things in a very open way and in a less technical way. So that doesn't mean the technical isn't there. It just doesn't necessarily help everyone. Okay. Detailed materials abound in terms of switching power converters. There's manufacturers' app notes and books and calculators. Having a webinar like this is not a substitute for reading the app notes to understand what they're saying. There are some very, very good books out there, but there's a lot of material and it takes a long time to go through it. So if you understand what you really think you're doing ahead of time, it makes it a lot more understandable and fast. You oftentimes just can't see the forest for all the trees because there is so much information out there. And when you're making a design, you need to scan for potential problems fast before calculating a solution to fix them. Again, a new box of vantage points is what we're offering. And need to think about how the old boxes may be confining you to looking at things in a way that's not the optimal way. 9.Connects are always here to help you should you run across situations that need some special expertise. So feel free to contact us. That's what we do. Okay, today we're going to talk. We're going to talk about a bunch of our resistors, inductors, and capacitors are not all perfect. Nothing is the ideal component that you study in class. And when you're talking about very slow speeds and very low currents and other such things, the approximations work very well. I mean, a 10K resistor is a pretty good approximation of a 10K resistor. And a capacitor, a 10 microfarad capacitor is a good 10 microfarad capacitor usually, as long as you don't exceed the voltage and break it over, of course. And inductors, well, they're those unknown things. They're a coil of wire and some magnetic material that people don't understand. But really, all of these parts do work fairly well at very low speeds. When you start getting up to high power levels, and you also start having very, very fast switching speeds, all the parasitic effects in these things can come to be a great problem. So we need to understand those. We also need to understand what we're trying to do with voltage and current sources. Most power supplies, we expect them to act like an ideal current source or an ideal voltage source. but they just don't do that. So we'll look a little bit at that, not a lot right now, but we'll touch on that. And then we'll also look at some buck and boost basics, and probably even try to do a quick simulation of one or two, depending on how the time goes. And there are some extra things that I think might be of interest we'll throw in at the end. Okay, let's just throw up a teaser here. You have an inductor, right? You bought it, and it's got a single loop of wire on it. And you say, well, that's great. This is going to be a wonderful component because all the magnetic field is completely contained within it. Well, okay. So you start stimulating it. You put, in this case, let's say you put 200-volt peak-to-peak AC onto this coil to try to magnetize it, because that's what this inductor is supposed to do. Well, guess what? If you look at it, you will note that at a particular instant in time, if one of the wires has plus 100 volts and the other has minus 100 volts, well, guess what? The wires themselves actually are charged positively on one side, negatively on the other side, and hence you have created an antenna. And that will radiate an E-type field that can get you into a lot of problems. Even though the magnetics is pretty well contained by virtue of it being a toroid, the way it's wound by having just a single turn all the way around is a single winding wound multiple times all the way around, what can get you into trouble. So things like that are not always obvious to people, but if you're looking for EMI problems, you might end up finding one of those. So the basics of inductors, I'm sure you're familiar with. They're the unforeseen part. We all know that we take a resistor, and if you put a voltage across it, the voltage causes a current. It's a direct linear relationship. We tend to also know that if we squirt current into a capacitor, that the capacitor tends to charge up. The inductor is very similar to a capacitor, but it works the other way. If you apply voltage to an inductor, then the current will ramp up. So if you have a voltage, like look at the equation over on the right, the equation over on the right shows us that if you use a voltage for a period of time, you have a voltage impulse that you've applied, and that will give rise to a change in the current level. And the ratio by which that happens is specifically the inductance. Okay, you can rearrange that equation to say that if you're actually starting to change the current through something, the rate of change of current with respect to time times the inductance will give rise to a voltage. So if you had a current source that was squirting a varying current into an inductor, well, then you could say what voltage would it be developing across that inductor? It's kind of like if you're saying you have current going through a resistor, what voltage would it develop? The same thing is true with a current going through an inductor. It's only that it's sensitive to the rate of change. So what else about inductors? Voltage across a conductor causes a current to flow, right? And if the flow of that current causes a magnetic field in and around the conductor, then that means it's going to be storing energy and hence require the energy to build. If you, the more current you have, the more field you have, and therefore the more energy will be stored in that. The energy goes by 1/2 Li squared. Very similar to a capacitor, which is 1/2 CV squared. So the 1/2 of the capacitance times the square of the voltage gives you the energy in a capacitor. Inductors are the same, except they do it with current. In other words, it's 1/2 the inductance times I squared. You'll start to see this duality between capacitors and inductors, where voltage applies to capacitors and current applies to inductors. But you'll see them over and over and over again. This duality will come up. And again, the definition of inductance is basically if you put an impulse of voltage, i.e. a voltage times a period of time across the inductor, well, how much does the current change? That's really what you're coming to in terms of the inductance equation. Okay. Alrighty, let's talk about some other things. Okay, I'm going to try to do some hand drawing here, so we'll see how well this goes. I have some other slides I can bring up at the time. Okay, I'm an observer, and let's assume that we have some empty space. Okay, take a pen. This is empty space. Into this space, we're going to insert some charges. Well, let's start off by inserting a positive charge. There's a positive charge. It's a proton, okay? And then somewhere else, right now, at this point in time, there is an electric field. The electric field is radiating out from a positive charge, we could say, but it doesn't cause any forces because it's not interacting with anything, because there's nothing else in the universe. But alongside it, we can say, well, let's bring up another proton. It also has this electric field. But once they're in the same space, and we're going to ignore, for the current time, all of the relativistic kind of mechanics and say, well, it's going to take time to come and go. You'll also find that inductance and capacitance, as you get very high frequency, tend to be related to relativistic effects. So, but if we do this, you're going to see that because there's two positive charges, we now have a repulsion between them. Very simple thing that always happens. And also, we'll note that that force is proportional to the radius squared, inverse of the radius squared. Now, if the charge were not there, it wouldn't be that that way. You wouldn't have that repulsion. Well, what if we just came in and decided that instead we're going to put in a negative charge? Simple review. Negative charge has electron, let's say, has a field in the opposite direction. Well, in this case, we are going to be generating an attraction. And that force, in each case, now, again, the force is going to be proportional to 1 over r squared between these two. That's the distance we're talking about. This is r. But note that it's an attractive force instead of a repulsive force. If these particles are free to move, then the electron and the proton would tend to be attracted to each other. Now, they could actually sort of smack into each other and form a hydrogen molecule, but they could also just kind of spin around each other and then go off in other directions if they're not close enough and they have too much energy. Also note that I'm talking about proportionality. Really, we have to talk about what is the charge on each particle. There's a negative charge on the electron, and there's a positive charge on the proton. So we end up with basically an epsilon naught and a Q1, Q2. The product of the charges goes in there, and there's an r squared. So there's other things that come into play. But the interesting thing is to just remember that in many cases, various charges might be far away from something that's happening, and hence would be able to ignore things. As you bring a charge closer, note that it's going to require more and more and more force to make that occur. So let me go back to here. Okay. I actually should just do an erase. Okay, no background. That's all right. So what ends up happening, let's talk about it again. If we have a proton, and we actually take this positive charge, as we bring, and let's say we take this thing and we decide we're going to actually nail it down in place so that it cannot move. Okay, we have a proton now nailed down in place. As we bring another proton in to get close to it, there is a force. And as the closer we get, it's going to take additional amounts of work to be able to bring that charge close to the other one. So first, it doesn't take much energy. But as you get close, it takes more and more, until when you get close, it goes very high, very, very high. If you're on the other side and head down, it's like going downhill again until you end up with a proton, say, far away. It's exactly like climbing an energy mountain. you can imagine someone who is actually trying to walk uphill and it's getting steeper and steeper and steeper, you have to push harder and harder and harder to get these charges to come together. And when you do that, you put in work. Therefore, that's where the energy comes from. And the energy, basically, if you take it from infinity, it's proportional to the charge over the square of the radius, as we saw before. So the force we have is, again, proportional to the product of the charges and the radius between them at any instant in time. And it turns out that also is proportional to the voltage that we have. The energy itself, to write it in a more formal way, and if you're not familiar with the math, that's okay, we're not going to do it, is basically an integral from being far away, i.e. at infinity, to however close you get to a part of this force. So as you go in, you add up this force, that's how much work you have to do. For a little bit of distance, distance close to the peak, you have to do a lot of work. For an equal distance far away, you don't have to do a lot of work. But there's a total amount of work that has to be done. Okay, this is going to become a little bit more interesting later. I'd kind of like to show you something in the meantime. It's been a long time for many of you, a number of you, the old-timers, but I wanted to give a quick idea of how these charges work. When you're talking about how electromagnetics work, you kind of have to understand both the electric field repulsion and attraction, and you also have to understand the magnetic field. Magnetic field is a little bit more esoteric, a little harder to understand. So let's start with something that originated a long time ago when these things were less understood, because it really is a fairly interesting idea, the way it was actually made. So let's say that we actually have a vacuum. We'll actually make a little tube, and we're going to suck the air out, and we're going to create a vacuum. All right. It turns out that if you get a wire hot, you take a wire and you connect the wire to some kind of an energy source. I'll draw it as a battery. And you get that wire hot, you're going to find out that it's going to want to drive various things off. Well, if you look at it, if you have an atom somewhere, let's say you have a nucleus with some neutrons in it, and you have a nucleus with some protons in it that are a positive charge. And let's say we have two of these. Okay, so we have a couple of nuclei. Then you end up with some electrons orbiting around it. So these are the little electrons that are out there orbiting around. Now, what happens is these atoms that you have are oftentimes bonded together into some kind of a molecule, or even a larger structure like a crystal. As you add heat to this, it starts to cause these molecules to vibrate. Well, guess what? You can vibrate it so much that it can start to fly apart, because all that heat is being stored in the intermolecular and interatomic bonds, and they are actually vibrating and passing this energy back and forth between each other. That's kind of some of the fundamental theory that comes up in when you study gases. So let's assume you get this very, very hot. What is going to happen? Well, the outermost things are going to fly off. And what are the outermost things? They are electrons. The electrons actually come loose. Now, granted, the atoms then become charged and try to suck the electrons back, but it turns out if they are tied to ground, if there's a ground path, then more electrons can be provided from that source, and you end up with the electrons hovering around out in space, and some are recombining and going back, and some are not. But this is basically just a big electron cloud. Okay. So what do you do with that? Well, you could conceivably decide that you want to play games with those electrons and come in here and put up a large metal structure and say, well, all right, let's put this to some kind of a very large voltage source, something that's very positive, and what happens to those electrons? Well, those electrons are then going to be attracted and they're going to flow. So current will flow. So we have negative current flowing. Remember, electrons are negatively charged. So positive current is taken to be the other direction, but really it's only electrons flowing. Nothing is flowing the other direction. Okay, so what happens if we decide that instead we're going to take this and make it a positive voltage? If it's a positive voltage, the current is 0 because all of the electrons in that case are repelled. And this turns out to work very, very well. This is a simple vacuum tube rectifier. Later on, they found that they could do some things very nicely. For example, they found that they needed some kind of resistance wire in the heater, so they could isolate everything by running the heater independent of the metal that was actually emitting the electrons. So they added something called a cathode, and the cathode was usually tied to ground. And what would happen is it would get hot with respect to the heater because the heater would heat it up. And they also treated it with thorium. Now, thorium is radioactive. So the radioactive portion of that meant that it also wanted to throw out even more electrons. It highly ionized the surface. So the electrons coming out were a lot higher. The goal they were trying to do was to get a lot of electrons so they could get a lot of current flow so they could get a lot of power. Okay, so, and then to control it, they added in a screen of wire in front of there, which they could attach to a negative voltage. If they made that sufficiently negative, the electrons would see the negative charge and actually stay where they were. But if that instead went to ground, then the electrons would go through. And once the electrons went through the grid, then they would be attracted to the plate. In order to make, it turns out that they would be going at a very slow velocity, so you still didn't get a very high current flow. So they came back and decided, well, we can fix that by putting in another screen here that is positive. So they tied that to the positive up above, and that allowed the electrons to actually become accelerated, highly accelerated, as they went through. Some of them would actually get stuck on the screen, and actually there would be a current flowing out, negative current. But many of them would be accelerated, and hence they could rapidly make it up to the plate. So they got high current flow. But then they found out that they were actually striking the plate with so much energy that they would actually bounce out more E minuses, and these little electrons would be bouncing out, and they would end up clouding up the field, and you wouldn't get as much flow. So the last thing that they put into it was actually what they call a suppressor grid, which had a negative voltage on it, that basically meant the electrons that bounced off the plate would actually be pushed back. So this is the theory that was going on about a century ago when electronics was being born. People were actually playing with electronics and actually playing with metals and the surface functions to try to get that to come out. But it does give you an idea of how the fields actually work and what you have to think about in many cases. Let's talk about get a little bit more into some special things that are going to be important for the discussions of power supplies and understanding the components. Okay, first, let's talk about dielectrics. Okay. Does everyone know how dielectrics work? Well, very similar to what we just talked about. Assume that you have a nucleus that has protons in it, and it has the neutrons in it. sorry. I'm drawing the protons as red and the neutrons as black, and I said that backwards. And it also has electrons around the outside. This is a typical dielectric material and how it's made. Note that the electrons are negative. Now what happens when you're doing this is, let's assume that you impose a voltage across this dielectric. What happens? Okay. Well, let's say that we actually put some kind of a conductor on each side of this dielectric, and let's assume that we charge one of them. Let's charge one of them negative. We'll add some extra electrons here. And the other one we'll make positive. We'll make it positive by actually removing some of the electrons and leaving the charged atom nuclei there. And that's how electricity works. It's actually the absence of electronics that constitutes positive charge in conductors. Okay, so what ends up happening? There's now an electric field. And the electric field is basically attempting to attract negative or force negative charges towards the top and force positive charges towards the bottom. Well, it turns out the nuclei are fairly well fixed in the crystal lattice, but the electric fields are not. Instead, what happens with the electric fields is they become distorted. The electric fields are now have a preponderance. The electrons spend more of a time a little further away on the other side of the atom. This actually turns the atoms into very, very tiny dipoles. This is the plus, and the minus is here. Okay. And that happens on all of them. I won't bother to draw it for the other two. But note that as you put a positive and negative charge on things, you put a positive charge on here and a minus charge on the top, minus charge on the bottom, the dielectric, the atoms in there, respond by polarizing themselves to reduce the amount of total field that is built up. Hence, you have to put more current into it to get the same voltage out. Well, isn't that what a capacitor is? If it's a big capacitor, you got to put a lot of current in to get much of a voltage rise. That is how the dielectrics work inside. All right. Well, what about the other materials? Let's talk for a moment about the magnetic materials. They work on a slightly different philosophy. Yes, there are atoms, and inside the atoms there are electrons. But what ends up happening is the electrons in there have a spin, and magnetic materials have the ability to have electrons with multiple spins of the same kind and align them through some quantum mechanical properties. I'm not going to go into that because it's too much. But the little domains of each one of these are all pointed in random directions. So if you said, what does this actually look like? It looks like they're little, think of them as magnetic domains. Think of them more like little compasses that say which way they're going. And they're pointed all in different directions. So you'll see all these little compasses aligned in different ways. Now, when you come along and you actually put a magnetic field into here, what's it going to do to all those little bar magnets? It's going to align them such that in the end, they're all going to be aligned in the same direction. Now remember, there's little domains, they're kind of affecting each other too, so they don't all align at once. It takes a little bit of force to do that. You have to have enough current flowing to create enough of a magnetic field to actually get them to align. But if you do that, they will align. At some point in time, they'll get so aligned that they can't align much more. And at that point in time, the material saturates. So in essence, what do you have? you now have a magnetic material that can respond to the applied magnetism and actually accommodate it. It can actually compensate for it in such a way that it doesn't give rise to as much stored magnetic energy. It's an entirely equivalent process to what's going on in the dielectrics with capacitors. Okay. I'm going to start, I think these are kind of some preliminaries that we needed to get out of the way. We're going to talk a little bit more about things like this before we get into real components. But I think it's important to know that you can already start to see why capacitors at some point in time could fail if the voltage gets too high. You can also see why magnetic materials will saturate. And these are some of the things that need to be understood. It also means that as they do that, they become nonlinear. And those are some of the effects that can cause a problem. Okay, so one thing I would like to show is that when currents flow in something, if I have a wire and current is flowing in this wire, we have some current flowing, it's going to create a magnetic field around the wire. And again, I'm drawing it backwards because the current is to the right, so it's always the right-hand rule. So by the right-hand rule, your thumb sticks in the direction of the current, your fingers curl the way the field goes. So if the current's going to the right, then the field, yes, the field would be curling around this direction. I actually did have it right. Okay. Now it turns out that the further you get away, this field is going to drop off. How it drops off is of very much importance in EMI, and so you have to ask the question, how does that work? If I have if I have just a point source, let's take it, and current and voltage are very analogous here. Let's say we had a point source, and let's say I put a voltage on it, and there's an electric field. How does that field drop off with distance? Well, it's actually a point, and therefore in 3D, this is a sphere. Therefore, the electric field, any sphere that I put around this, all the lines will go out through there. If I make a larger one, all the lines still go out through there. So the same amount of flux is going out through every sphere I put around that charge. But guess what? The area of the sphere is going up like the square of the radius. If I have a radius, the area is proportional to the radius squared. Therefore, what is the field density, the number of lines per square unit of area as the radius goes up? Well, it's the same number of lines everywhere, but the area is going up like the square, which means the electric field falls off like the radius squared. If I could invent a hypothetical piece of wire, here's a piece of wire that's infinitesimally short, and if I could make charges suddenly come into existence at the front end, go a short distance, and then annihilate themselves so that I don't have to worry about a whole current path, it turns out this little infinitesimal bit starts acting very, very much like the electric fields. Trouble is that electrons don't tend to create themselves and annihilate themselves. At least we don't experience that in our everyday life. So we end up having to talk about a whole wire and a current, which makes it sound quite a bit different. If we had a whole if we had a bar and we charged up the whole bar with a total charge of Q, then it'd be like having little Q's all the way along, and the net of the field that we would see derives from that. So I think you can see this. Here is an ideal wire. It's got a length and it's got a cross-sectional area. It has several things that are not quite right about it. First of all, it doesn't have a zero resistance. It has resistivity, unless it's superconducting. But even with superconducting, there's a current threshold where you can't go over that. It just can't conduct it, and then it does become resistive. So in reality, it is a resistive. It has resistivity, and that turns out that it's going to be the length times the area. If you take the length of the area ratio multiplied by the resistivity, you'll get the resistance of that length of wire. What else is wrong with it in terms of being an ideal thing? Well, current through it causes a B field, a magnetic field which stores energy. Hence, this wire has inductance just by virtue of its length. So anytime you connect something through a length of wire, a length of conductor of any kind, you're automatically getting an inductance into it. Further, in green, you'll see something called a self-capacitance. People are used to thinking about a capacitance being between two plates, two things. Well, those two things actually are mutual capacitance. But if, let's say, you had a sphere and you had two spheres, one outside and one inside. If you calculate the capacitance, and then you let the larger sphere just get larger and larger and larger until it gets huge, i.e. it approaches infinity, its effect becomes nil. And in the real world, you actually have self-capacitance to a wire all along its length. All of those things mean that that wire is going to have difficulty passing high frequencies above some point. It's going to have impedance stopping it. It's going to have capacitance that is also trying to short it out. It's like an LC-LC filter down its entire length. So that's something that we really need to kind of understand as we get into talking about high-speed switching things, because the leads coming out of transistors and ICs and things all have those effects. Let's talk about capacitors for a second. Capacitors themselves have equivalent things. They have series resistance in them. The series resistance actually is in series with the wires, which are part of what's stopping you. There's the inductance that's again part of the wires. If you have something that is a rolled foil capacitor, where it's actually been rolled up to get a lot of surface area, those things tend to have a lot of capacitance because they're not perfectly balanced. So some of the current actually swirls around in a circle, and as it charges and discharges. So different kinds of capacitors have more or less resistance. They actually make, like 0805 capacitors are long and skinny. They make 0508 capacitors, which have the pads on the short ends, so that they're very narrow because they have much less inductance. Those things are very important at high frequencies. In here, you'll see a little schematic that shows a big electrolytic capacitor, followed by a foil capacitor, and then a big and tiny ceramic, and then including the two middle layers of the board as a capacitor. If you look at those, they all have different amounts of resistance and inductance in them that actually makes them have an impedance at high frequencies that makes them no longer look like capacitors from a series standpoint. Above some frequency, they will all start increasing in impedance instead of decreasing. But if you take all of them and put them in parallel, then the net parallel sum of those becomes what you see in the red line. And you can actually make something that has a fairly low impedance across a wide range of frequencies. And that's what you're trying to do when you put capacitors into a circuit. Back when everything was small and TTL, everybody always put in a 0.1 microfarad, and they put in hundreds of them. But as speeds went up, those capacitors were no longer good for the high speed. When you have stuff switching in the gigahertz region, a 0.1 microfarad is almost no good at all. So it's important to understand the different things you have. Notice that you also have the ability on printed circuit boards to have a ground plane. Remember that at some point in time, the size of the ground plane becomes significant, like a half wavelength of some of the frequencies of interest, and then it can actually turn into an antenna and have high impedance again. Okay, all right. So how do these things work? At what point in time do fields actually become, fall off and become, at what rate do they fall off? If you have a wire, if you look on the left-hand side, you'll see a wire with a current flowing through it. Okay, there we go. Okay, so on the left, you'll see a horizontal wire. There's current going through it. There are lines, field lines, magnetic field and electric field, that actually radiate out from it. In a long wire, those radiate straight out, and it only falls off like 1 over R if you're close to that wire. Now, when you get close to the end, it starts to bend over, and outside of that, it starts to look like 1 over R squared. That's because it now is looking like an end, and it can actually use some of the horizontal motion instead of just the vertical motion. And if you ask, well, where does it change from falling off like 1 over R to falling off like 1 over R squared, it would be if you took basically a 45-degree cone from the end of the wire. And within those two cones, it's going to be falling off like 1 over R, predominantly. Outside of that, it's going to be predominantly falling off like 1 over R. When you're close to that boundary, it's sort of mushy and in between. So just understand that being the case. Down below is a figure that's a little hard to see, but it actually is a parallelogram. It's a flat plate intended to represent that. And above that, in red, you will see a pyramid. And that pyramid is actually the area above a plate where things only don't fall off at all. They're constant. You'll notice between the two plates of the capacitor that the electric field is constant. When you get outside of that, there's an area where it falls off like 1 over R, and when you get sufficiently far from the plate, it turns out it goes up like 1 over R squared. I wish I had more time to show that to you. The exact same analogy on the right-hand side happens with the B field. When you start talking about a plate, you can have a line, and you can have the magnetic field, which is now circles around it. And within that same area, over on the right, you'll see that if you have a wire, you get lots of lines circling it. And as you get further and further out from that line, it's going to fall off. But again, in this area between the two cones, the B field is going to drop off like 1 over R. And when you get way outside of it, it falls off like most electromagnetic fields at a distance. When you get into far field areas, it falls off like 1 over R squared. And again, if you had a sheet of current flowing, let's say you had a large number of wires that were very side by side, and you forced the same current down all the wires so that it acted like a sheet, you will see the same pyramid. And in that same area, you'll find that the magnetic flux, is constant. It does not fall off across any of that distance. So these are important things to think about when you're doing ground planes. We're getting a little bit close to the end of our time, so let's see. I kind of wanted to get into a kind of a simulation here, and I'm not sure if we're going to have the time to do it. I did have another thing I'd like to show you briefly. These are air core inductors. A typical air core inductor has the coil. It actually is this piece of wire. As you run the wires around and around in loops, as you see in the lower right-hand corner, you'll see that in between the loops, the field is going in opposite directions. That tends to cancel the field. But through the center of the whole coil and around the outside of the coil, all the field lines from all the individual wires are going in the same direction. So they tend to add. The net effect is that you have one large magnetic field going through the core and going around the outside. It has parasitics as well. If you look at the diagram, you'll see that there's series resistance in the coil. There are two kinds of capacitors in there. There is the coil-to-coil, winding-to-winding capacitance. There is also the self-capacitance to infinity, which is just because as you charge up a conductor, there's a field that goes out to infinity. All of those things come into play and cause there to be a frequency above which the inductor does not look like a very good inductor. At low frequencies it does, but at high frequencies it doesn't. So one way that they help improve this is space the coils further apart, put a gap between them so that the interwinding capacitance goes down. They also tend to use fat wire, or such that they have less resistance in it. So it basically keeps the Q up and lets it operate up to a higher frequency before it starts to roll off. You will see that these things can be calculated, they can be used. If you start taking this coil and bending it around in a horseshoe, you'll start to see that some of the lines that come out of one end, they go back into the other end, but now they can kind of just jump back into the other end. If you keep bending it around a complete circle, you'll find that all of the lines that are coming out get captured. They don't go around the entire coil. What comes out of one end goes right into the other end because they're right next to each other. As a result, when you get a toroidal-shaped winding, all of the magnetic flux, except for a tiny bit that escapes, all the magnetic flux stays inside the coil. What that means is that toroidal cores are intrinsically self-shielding. The magnetic field doesn't get out of them. That's very, very important for shielding things. It's especially important at very, very high speeds, and switchers are now getting up to very, very high speeds. So what we have here is a typical converter. This particular configuration is intended to be a buck configuration. I actually have this set up to simulate, and it looks to me like we're going to be out of time to run the simulation. We could keep going a little bit longer. Okay, we'll keep running a little bit longer. So let's talk about this a little bit. Let me make sure I can get my drawing tool up and over the top of this. What ends up happening is we start with a voltage source. The voltage source itself is variable in some cases. In this case, I haven't implemented a feedback system in here to try to regulate the input based on how the voltages in and out work. This is basically configured to output 3 volts if you have 5 volts in, based on a duty cycle that is specifically set by pulse width modulation. In the real world, we would take this one step farther and then actually make a feedback loop to make that happen. In general, what we want to do is take the voltage and chop it up in some way and spit it out into the load. First thing to notice about this is that if you have some kind of power in, and if the efficiency is very high, which it isn't, I mean, it is high, but it's not 100%, it's close. Well, that means you'll have power out will be the same because you won't be losing anything. So if I have 5 volts at, let's say, 3 amps, because it makes the math easy, then and if P out is 3 volts, then that would be 5 amps. Well, it's whatever it is with the load. The load will decide how much it wants when you put 3 volts across it. So the load will determine that, but it will draw whatever it needs. But the 5 volt to 3 volt is being stepped down in this converter. So how does it work? Well, it turns out there's several things to notice about this. In the beginning, we end up with a filter. And the filter is pretty much to keep the current into the source from being well behaved. We also include a resistor just for simulation so that we can see what the effects are of that if there's some resistance in your inductor. Now you can actually put that into the SPICE simulation of the inductor. I tend to like to have it as a separate component so that I can play with it and see what happens if I'm designing the inductor. We also, turns out that this will be a very resonant structure, so we're going to end up having to have something to try to damp resonances. We can talk more about that later. What ends up happening is current flows through the inductor, flows out of the source, through the inductor, and into the capacitor. And of course, as it's charging that, current also returns to this. So this capacitor, C2, charges up. At some point in time, the Q1 is going to turn on, and it's going to actually allow the voltage from this point to be connected through to the input of the inductor. And current is going to start flowing. When the switch switches off again, The inductor is going to keep that current flowing and has to pull it from somewhere. So it pulls it up through the diode. So the current in the output is going to continue. It's going to have a DC component going through the load, and so most of the AC is going to be going through the capacitor, which acts as a filter for the current to keep the voltage on the load constant, to get rid of the ripple. And of course, as it flows out of there, it's going to be coming back to feed the inductor path. Except when the switch is on, where does the current flow? It's a little bit of a different path. The current in this case is going to actually flow out of the input capacitor, out through the output, and down through the load, and back. Now there's two very, very critical things in power supply that we're going to come to over and over and over again. So I want to basically reiterate them here. There are two things that happens. There is one node in the switcher where the voltages are going up and down very, very rapidly. Okay? So let's go ahead and highlight that. Where is the switching node? Where is the voltage going up and down a lot? Well, it's where this switch occurs. The FET is one switch, and the diode is the other switch. You could use a FET for this diode, but this junction between the two switches and anything else that is attached to it, that is the switching node. That is something that will radiate very, very significantly. And it will radiate an electric field because the voltage is changing very fast. And if that's a long node, it has a lot of area, a lot of space on it, it's going to have a lot of capacitance to the outside world, and it's going to radiate a lot of energy. So you want to keep that node very, very, very small. There is another node that is very, very important, and that is where the current switches instead of the voltage. Well, notice that some of the time, the inductor in the output is going to keep the current flowing, but some of the time it's going to be flowing through the diode, and some of the time it's going to be flowing out of the capacitor. So some of the time it's going to be flowing out of the capacitor, and some of the time it's going to be flowing up through the diode. The ground from the bottom of the diode over and up through the capacitor forms the other part of the loop. Okay, so this is the current loop where current is going to be changing. Some of the time it's going to be flowing on one side, some of the time it's going to be flowing on the other side. And you have to understand that when current flows on one side and then switches to flowing on the other side, that you're going to actually have an AC current in the loop. If that loop is open, it's going to radiate a magnetic field. Or I guess I should, by rights, call it an H field, not a B field. But so the goal here is to try to say, when we design this, we're going to want to make that loop very, very small in area. In fact, we would like to make it such that the current flowing on one side of the loop flows directly in the same path as the one on the other side. If we could take one of the loops and actually make it lay right over the top of the first one, then there would be no area, and then we would not have that H field radiation. H field radiation induces currents in all sorts of other circuits nearby. E field radiation, and especially low impedance circuits. E field radiation tends to impart voltage noise into other circuits nearby, especially high impedance ones. So we need to deal with these things a lot more. I'd like to do that simulation. Let's take a quick look at this. This is a simulation. You'll see in the top plots are actually of the current output. The blue is the output current. The red is the input current. We can see that the output current is higher than the input, which is kind of what we would expect. This is, by the way, this is only 6 millisecond simulation. In the middle, you can see what the voltages are doing. The input voltage was a source, so it starts at 5 volts and it's red. The output is in the blue trace in the middle. And you can see it's climbing upward and getting closer and closer and closer to 3 volts. And if you want to look at the power down below, the blue curve on the bottom is the output watts. The red curve is the input watts that are taken. And the efficiency is shown in green. You'll notice when it first starts up, there's a lot of surging currents and other things that happen, so the efficiency is kind of all over the map. As we get closer and closer to the end, you'll see that the blue and red curves are getting close, which means we're starting to get a moderately good efficiency. I think this one's running somewhere in the neighborhood of about 94 to 95%. If you look at the green trace on the bottom, and then you look at where 1 is on that, so it's basically 1 to 3, so 1 is 1/3 of the way up. You'll see it's very, very close to 1, and that's again what we're getting out of this particular converter. We should look at it more in depth. In a coming session, we also want to look at trying to use simulation and SPICE to handle some of these problems to see exactly how they work. It's great for handling the transient conditions especially. So, with that, I'd like to open it up for some questions. Anybody who would have some? I will. By the way, you can see most of these things if you drag it over here. In Altium, there's a place when you look at a particular component. You normally set it up in the schematic library, but you can't set it up in here. You can add a model name, and if you want to, you can edit the model. Let me drag that screen over. And you can see these are some of the internals that are built in. This is called a resistor, and it doesn't have too many parameters to it. It has a value parameter that I've made visible outside so that I can change it from the schematic, and it has a mapping of the pins between the model and the port. So all sorts of R's, L's, and C's can be handled that way because they're built in. Also, a number of diode and other type parameters are in there to make it easy for the simple components. When you try to model more complex ones, you probably are going to need a subcircuit. So in a case like a FET, these are items that you would normally get from the manufacturer of the part. You can build them yourself, but it does take a little bit of work to do that. This is a SPICE subcircuit, so if I were to look at that, I can see how it's called out. I can actually see what the model file looks like in its standard SPICE code. We're not going to go into that today. It also has extra parameters you could show if anyone. This one doesn't have any that you can adjust from the outside because the FET acts like the FET. Also, the pins, the drain gate source in the component, and the pins have to be mapped, so they're shown in here. All of this is editable, and you can set it up. And can't get into everything, but okay. First question I have: what do you consider high speeds as it relates to switching power supplies? Well, that's a good question. Let's start by defining. There is the main switching speed, which is how often it makes a complete cycle turning on and turning off. And obviously, there is a lot of energy at or around that frequency and harmonics directly above that. So if I have a square wave at 100 kilohertz, then I'm going to have a lot of 100 kilohertz energy and 300 kilohertz energy and 500 kilohertz energy for mostly the odd harmonics. And so you're going to have quite a few, probably at least 20 harmonics to deal with. The problem is that there's another set of harmonics that's even more critical, and that has to do with the slope of the rising edge. If you have a single edge all by itself that goes from low to high, but it's going to go from low to high very quickly, then it's going to take a lot of high-frequency energy to make that transition occur. If you were to look at that and decompose it, you would find out that it has to do with the slope of that curve. And there's all sorts of rules of thumb, and different people pick their favorite rules of thumb. Be my guest to pick whatever you like. But I'll give you an intuitive thing, because that's what we're here for. If you can imagine a signal that's going along low, and then it slopes up at some slope, and then it's high. Well, if you could take a half of a sine wave that goes from low to high, and in the middle has some slope, if you could just fit that sine wave in there and say, okay, it starts out at 0 slope at the bottom, it ends at 0 slope at the top, and in the middle it has some vertical slope, it has to go up that height, the frequency that little half of a sine wave is, it fits right in there, that's very, very close to what you would consider to be the fundamental of that frequency. It's as you would expect. You have to have something shaped like that, then you have to have a third and a fifth and a seventh harmonic to actually make the shape look like, to have the sharp corners there. Now, if it can be rounded off a little, then you can cut down some of the harmonic energy. But note that the rising edges are a much shorter period of time than the overall waveform. So even though the waveform may be switching at 100 kilohertz, it may be the edges are transitioning and creating frequencies well up into the gigahertz region. And that's what you need to watch for when you design the filters and the switching, are usually the switching edges. And that energy, when it's created by a part turning on or off quickly, will actually cause all sorts of ringing in the other components. The inductors will have their stray capacitances, and the capacitors will have their stray inductances. And the whole LC network of all those stray things will sit there and resonate, and you'll get little spikes and jiggles as a result of it. And that's what you see in the real world most of the time. Okay. I hope that answers the question. Can you show us your basic boost topology? I do have it. It's getting pretty late to go into that. I'd really like to go into them in a little more detail, and so I think we'll do that in the next one. There's actually a number of buck and boost topologies, and then there's a whole bunch of other topologies beyond those. So I think we probably need to have a good session talking about those different topologies and how each one of them works. So the answer is, yes, I can show it. I will show it. I just think now is probably not the time to go into it. So we're going to hold off till next time. Another question, shouldn't the output current have been less than the input current since Vout is less than Vin and Pout equals Pn? Well, I believe it was, but maybe I got my colors wrong. Let's take a look at that, okay? All right. So the output current is higher and the output voltage is lower. So we have one higher and one lower. The input voltage is lower, and the input current is lower, and the input voltage is higher. Because it's going from 5 volts down to 3 volts, the input will have a higher voltage and a lower current. The output has a lower voltage and a higher current. So they're not both high in the same case. So if you look at the two blue lines, you'll see in the upper trace, the blue one is on top, and the lower one, the blue one, is below the red one. And so they actually come out to be the powers you see in the bottom trace. So you can see the red trace is the power from the input, and notice that there's a little bit of ripple on it. And then also the power from the output is right below that in the blue line. And actually the efficiency is calculated from those two, and you can see it's running somewhere in the neighborhood of about 90–95%. And if they had been higher, if it had been lossier, such that they weren't very equal, then that would not have been right around 1. So it is. Okay, I think we have another couple questions here. Current into and out of C2 must be 0. That is correct. Current through the diode is one direction. So do you really have a loop? Can you clarify how one counters the others? Okay, that's a very, very, very good question. Let's talk about that. Let's go back to the schematic. When we talk about the current loop, there is a net DC power flow through the system. So we actually have power that's actually coming out, and there is power coming out and flowing in a DC way through into the output. When we talk about this, we talk about the loop, we're only talking about the AC component, okay, or the switching component. It's not really true, just alternating current as in sinusoidal. In other words, there is a point in time, if you just watch this on a transient basis, the current is kind of always flowing into the capacitor. but the net flow through C2 is never going to be a DC. But when a slug of current when Q1 turns on and takes a slug out of C2, it's probably going to droop a little bit because L1 is keeping the current fairly constant on the input. So it will actually decrease a little bit in voltage. Now when Q1 turns off, then L1 will continue dumping current into Q2 and it will charge back up. So we end up having a ripple on Q2. The net DC stays the same. The net charge, net voltage stays the same, but energy is rippling in and out of Q2. Okay? Now the current that flows through Q1 is going to be interrupted. When it's interrupted, L2 is going to continue to want to draw current. Where is it going to get it from? It's going to suck it up from ground. So that the top of the diode will actually go to about minus, this is Schottky, so it would be about minus 0.4 volts, minus 0.5 volts, something in that region. And then when Q1 turns on, it's going to take basically 5 volts out of Q2 and apply it, 5 volts. So the high voltage is going to be plus 5.0 volts. And the diode is going to be reverse bias. So there's a sudden switching of current from being sucked up from ground to being sucked out of the capacitor. When it's sucked out of the capacitor in turn sucks it out of ground. So ultimately it is all sucked out of ground. And that's why there's a DC flow in the ground path. I hope that kind of answers the questions. What about back EMF generated by the load? Yes, the load itself, in this particular case, we only have a resistor. If we had an inductor in the load, okay, we could also have some AC effects that would be reflected back. But in general, what this is saying is we have a constant current flowing. Because we have an L and a C, we basically get a constant current flowing, and that current is attached, basically flows down through the load. Now there is a little bit of variance here. There's a small amount of ripple in L2, but it turns out that the load voltage is also being filtered by capacitor. So V out is pretty constant. If V out is constant, then this end of the inductor is going to be fairly constant in voltage. And if it keeps a fairly constant current, this voltage at the switching node is going to be changing radically. Again, remember that the switching node is going to be having a very large voltage change on it. So yes, we have back EMF. We have some AC form of back EMF from the inductance, but what that's doing is acting like an LC filter. If we didn't have that, then the switching voltage would be applied directly to the load, and the current would be going up and down the voltage